So our next distinguished speaker is Yiannis Aloimonos from University of Maryland Robotics Center. There's been a glitch into the connection, but I think we're almost set. Yes, I can see we can.
Almost.
Desktop, and it's one of those.
Sorry. Okay, thank you, Bruno. It's a real pleasure being here. I have many friends in this audience, and the robotics community is one of the coolest communities on the planet. So I'm very happy to speak with you. Okay. So now, what is in the mind of the robot? There's two boxes. One says perception, and the other says action. And these boxes are usually done by different people. Now, perception needs action, because perception is active. But action needs perception, because you have to see what you're doing. So the robots of the future will do many things, as opposed to the one thing that they do now, or they did in the past. And so we need a generative system to generate all these actions. What could that system be? Now, and thank you, Professor Nakamura, for the tutorial on mirror neurons. The mirror neuron discovery has changed the game in this arena, because understanding perceived action versus producing action is basically the same problem. And so if you have a theory about action, you can test it in recognizing action, because there is a very large number of data sets that we can take advantage of. So there are basically two structures in an action. There is the so-called correlational structure. You do one thing, and then you do another thing. And then you associate the next thing with the previous thing. And then you do another thing, and so on. So you make chains. This is how computer vision people today are trying to solve the action problem. But there is another structure in the action, and that's what we call the instrumental structure, and that is cognitive. Let me give you an example. Let's say you have a box which is locked, and you have a key, and you have money, and you want to open the box, put inside the money, and then lock the box. Now, no matter how you think about this problem, it has stages, as you see here. And depending on how you think about it, you can organize the different components and the sub-goals of the action in a different way. So if you look at this sentence, instinctively, birds that fly swim. They instinctively doesn't go with the next word. It goes with swim. That's what makes language difficult. Now, action is the same way, because you can see they pick up the money, it's going to go with the deposit money. So depending on how you think about it, you can see a compositional hierarchical structure in the action. This is the instrumental structure. And so on the lower right, you see the actions in a tree, and the blue actions are what you can call abstract actions. Okay, so the generative system that I have been looking for the past 15 years is, an example of it is a grammar. Of course, today people use neural networks to make predictions for the next thing, but that's like a parser as well, if you make the grammar probabilistic. So the grammars are not on the movements. The grammars are on the goals and the sub-goals of the action. So we developed this minimized grammar of action motivated by the minimalist program of Chomsky. And it has 4 rules. The A's with the primes are basically actions, and then you have goals and modifiers and tools and objects, and they are related in this context-free recursive grammar. And a number of paleontologists and neuroscientists have studied this grammar, and they applied it to the problem of napping. Our ancestors, Homo erectus, Homo habilis, they didn't have language, but they were making tools from stone. And in order to make tools from stone, when you work with two stones and you keep hitting, then you need a context-free grammar for that, because you have to remember all the time two things: what every hand is doing, because as you hit the stones, you keep manipulating them. So this is significant because if the Homo erectus needed a grammar in order to make tools from stone, he had that grammar ready, and it could have been recycled for language. So we also used this grammar to build the so-called cooking robots. This has sound. I don't hear the sound. Sorry. Yeah, it's all on, but okay. Sorry about that. So basically, what we are doing here is we are watching recipes from the internet where people are cooking. And by observing the activity that is taking place, we are building the parse tree of the actions with the goals and the sub-goals. And after we have that tree, we can give it to a robot so that it can implement the action. And this is exactly what you are watching here. And there is sound, but unfortunately the sound is gone. So after this phase, you have the robot execution phase, where you give now this information, and the robot is going to do what it saw. Or in the interest of time, I will advance. So you may say, wait a minute, where are the symbols? Where are the primitives? You have the grammar, where are your symbols? The symbols were discovered 100 years ago by this couple. They were going to the American factories and they were observing the American workers because they wanted to help them. So they wanted to know what they are doing. And so they figured out that when somebody is working with his hands, then he can be in a very restricted set of states. And they call these states verbligs, which is the name Gilbreth spelled backwards. So these are the verbligs in their own symbolism. So basically, transport empty when the hand is moving with nothing in it. Transport loaded, TL. The hand is moving and it has something in it. Grasp, hold, release, etc. And so what we did is if we made them functions and added spatial arguments. And so if someone is making a bowl of cereals and bread with milk for breakfast, you can turn this whole activity into this string of verbligs. Transport empty, moving towards the plate. Grasp plate, transport loaded plate table, you put it on the table, release plate, etc. So the ability to predict contacts, because if there is no contact, there is really no action. To predict contacts by hands and or tools and the relevant objects from the video allows us to translate from vision language to verblig language. And so we can use now this theory before we do actions to see whether we can recognize actions. And we did this here for predicting, for anticipating actions in a video. And you can see here, this is from the Epic Kitchens data set. and somebody is doing things, and we are building the object manipulation graph, depending on the things that you are touching. And that makes it easy to make predictions. And we managed to get the top performance on this. But we made a mistake, like most of you. We kept the perception and action separated. So we have to put them together. And the way to put them together is to do a little perception, a little action, a little perception, a little action, interleave them. And so, for example, if somebody is cutting the tomatoes and putting them into the box, you can turn this plan into this program that you have here. But it doesn't have perception inside. You have to put perception with various functions. So basically, the actions that I have been looking for, and I used all these different formalisms, are really programs. And these programs, they have both perceptual functions inside and motoric functions. The way to see it is if you speak to a robot and you ask it to do something, it has to come up with an action plan, like this program, to solve a problem. So you have a perception API and an action API. The perception API has various functions, some of which use large language models, and the action API. And now you can have these action plans as Python programs. So the thing with actions is that, with programs, is that they are compositional. You can take one, put it inside another, take a piece of a program, put it in the beginning, put it in the end, and so on and so forth. So I haven't told you that, but you can use LLMs. These programs, you can write them yourself. Or you can get help from large language models to generate them. And so applying now this theory, where the action is the program, and when you recognize action, you really recognize the program. Again, we are at the top place for the vision-only solutions. And so this is my last slide. I envision a future where all of us write the same kind of programs, and we give them to each other, so we can build a community. And so what's in the mind of the robot? It is these kinds of programs. Thank you.
Thank you so much, Yiannis. Maybe one quick question while Oliver sets up. Yes. Fourth row, middle.
Thank you for your beautiful talk. I wanted to ask, how easy is it to perceive accurately contact only from videos, especially maybe the low-resolution kind of videos that are available?
Yes, it is not very difficult. It involves, estimating time to contact and getting the signature of the acceleration when you make the contact. One other possibility that we haven't implemented yet in this is to use tactile sensors and have the information from there. But for the time being, the solution is based on vision, and it is, I would say, of a moderate difficulty. Okay.
Thank you again, Yiannis.
Thank you.